Dear students, today, we will study fusion reaction. A fusion reaction is one in which two lighter nuclei combines to form one larger stable nuclei with the release of energy. This is exactly an opposite to what happens in nuclear fission, but the amount of energy released is much greater than fission in fusion reaction. In figure, you can see two isotopes of hydrogen, one deuterium, and second tritium combines to form one helium nuclei with the release of neutron and energy. This happens because fusion only occur at very high temperature, usually inside core of Sun. This high temperature increases key etc. energy of nuclei, which enable them to overcome repulsive potential between two nuclei due to positive charges and allow neutrons to bond them in one nuclei by strong nuclear force. Fusion is more preferred than fission due to large energy, no nuclear waste, but it is not achievable yet at Earth due to requirement of high temperature and plasma stability. The amount of energy released in fusion reaction is due to conversion of mass defect into energy by Einstein's mass-energy equation. Mass of reactants in this example deuterium and tritium is greater than mass of products helium and neutron. This mass difference is mass defect, which is converted into energy. Let calculate mass defect. The mass of deuterium and tritium is given, whose sum gives total mass equals to 5.030151 U. Whereas the total mass of products is given by the sum of helium and neutron mass, which is equal to 5.011268 U. Mass defect is equal to mass of reactants minus mass of products. By putting a total mass of reactants and products, which we calculated above, we get mass defect, which is equal to 0.018886 U. This mass defect is converted into energy by Einstein's mass-energy equation. Here we put 1 U equals to 931.5 MeV c squared, then by simplification, we get 17.6 MeV, which is energy released per fusion reaction of hydrogen isotopes. But the question is here why we consider energy of fusion high as compared to fission, although in one fusion energy released is 17.6 MeV, whereas in one fission amount of energy released is 200 MeV. This is due to energy per unit mass, which is greater in fusion than fission. Let calculate energy per unit mass for uranium-235. Mass of uranium is 235 U, where 1 U is equal to 1.66 times 10 squared to the power of 7. By putting in relation we get 0.85 MeV per U for uranium. To convert energy into percentage kilogram. Simplify, by putting values for mass converting into kilogram and energy from MeV into joules. It comes out to 8.2 times 10 squared J per kilogram. Now do the same steps for hydrogen isotopes in fusion reaction. First find energy per unit mass by dividing total mass of reactants with total energy released per fusion. By simple division, we get 3.5 MeV energy per unit mass for fusion, which is much greater than what we get in fission reaction. Now, by converting mass into kilograms and energy into joules, we get energy in per kilogram. Energy per kilogram is found by dividing total energy released in joules by total mass of reactants in kilogram. It is 3.34 times 10 power 14 joules per kilogram, which is almost 4 times the energy released per kilogram in fission reaction.